Today we package eigenvectors into eigenspaces. Then compare two ways an eigenvalue can be counted, because one counting system was apparently too peaceful. For a fixed eigenvalue lambda, the eigenspace is the null space of A minus lambda I. So it is a subspace, not just a pile of unrelated eigenvectors. The zero vector is included, even though it is not a useful direction by itself. For this diagonal matrix, the x-axis is the eigenspace for lambda equals 2, and the y-axis is the eigenspace for lambda equals 3. The operator stretches each line but does not mix the lines. For once, the matrix behaves with basic social boundaries. Here the vector space is polynomials of degree at most 2, and the operator is differentiation. The eigenspace for lambda equals 0 is the null space of differentiation. So it is exactly the constant polynomials. Algebraic multiplicity comes from the characteristic polynomial. Geometric multiplicity comes from the eigenspace dimension. These two numbers can agree, or they can disagree. Naturally, the disagreement is where the plot gets rude. For A equals 2i, every vector is an eigenvector for lambda equals 2. The root 2 appears twice in the characteristic polynomial, and the eigenspace has dimension 2. Both multiplicities are 2, a rare moment of cooperation. This matrix has the same characteristic polynomial as 2i, but the eigenspace is only one-dimensional. Algebraic multiplicity is 2, but geometric multiplicity is 1. The polynomial promised 2 copies. The vectors delivered one direction and an excuse. A projection keeps the x-axis fixed and crushes the y-axis to 0. Here the two eigenvalues are 0 and 1, each with algebraic multiplicity 1 and geometric multiplicity 1. Not all examples are villains. Some just flatten things for a living. Eigenspaces collect all eigenvectors for one eigenvalue into a subspace. Geometric multiplicity measures the size of that subspace. Algebraic multiplicity measures how many times the eigenvalue appears as a root of the characteristic polynomial. Next, diagonalization asks whether these eigenspaces are large enough to build an entire basis. Spoiler: sometimes the answer is no, because matrices enjoy withholding information.